Yes. Today I discuss about very important about two important theorems in linear analysis: BOLZANO-WEIRSTRASS theorem and HEINE-BOREL theorem. Very important theorem in linear analysis. So I hope that after looking the video, you can very easily understand what the theorems states, and you can very easily apply in the problems in analysis to solve many problems. So let's start. First, we discuss about Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem says that for any bounded sequence, bounded sequence must have any bounded sequence must have must have must have a limit point or must have a monotone a convergent subsequence or limit point. Convergent convergent subsequence. In other words, you can say must have a limit point. Limit point. So first, before to prove this, I want to discuss about this point. Limit point. What is limit point? What is a sequence? Sequence is a one-one correspondence between natural numbers to be a function a function uh, a function defined sequence is defined as functions to natural numbers to real numbers. This is a sequence. Like I can say a function if n is equal to 1 by n is a sequence, and subsequence is a uh, any collection from the sequence. So this is the subsequence. And convergent means that the sequence must converge to a point. Means there must be a last point or at the point where the next point are the same with the point. Then this is called convergent. So limit point what is very important to understand what is a limit point. Limit point is that for any sequence if it converges, then it must have a limit point. Like these functions have no limit point. You can look this. If you put n natural numbers, n belongs to natural numbers 1, 2, 1. This is a exceptional case. This is also a sequence, but it does not have any limit point. 1 by 3, 1 by 4. You can test any test you can do. It does not have any limit point. This series sequence does not converge. It is a divergent series. If any sequence is not convergent, then it is a divergent sequence. Now let's see one more thing. If the function is defined in another way, I'm giving a bounded sequence. An example of bounded sequence. What is a bounded sequence? Take the function sequence is h. Fn is equal to n plus 1, n by n plus 1. So we wish to know, first I am calculating the points of the series. If you put n belongs to the natural numbers 1, 2, 3, 4, then what will be the sequence? It will be 1 by 2 first element. After putting 1, then will be 3 by 4, 2 by 3, then will be 3 by 4. So this is a convergent sequence. 3 by 4 dot dot dot. Where it converges if we take the limiting value, limit of fn where n tends to infinity. I am just calculating the limiting point of this function. So this is fn. You can write this in this way. Limit point n tends to infinity. This will be 1 by, after dividing by n, the numerator is divided by n, and the numerator and the denominator both are divided by n. Then it will be 1 plus 1 by n. Then if n tends to infinity, then this goes to 0. Then the limiting value will get equal to 1. So this sequence converges and its limiting point is 1. But the limit point actually exists in this sequence. Actually no. One is the limiting point, but one does not. You cannot find out one. Just it is nearly one, not equal to one. So you will get the points which is nearly one in this sequence, but not equal to one. So this is the limit point and this is the sequence. Now we'll prove the BOLZANO-WEIRSTRASS theorem. It states that any bounded sequence, this is bounded sequence since it is bounded below by 1. Its upper bound is half and lower bound is 1. Upper bound actually 1 and lower bound is half. It is a monotonically increasing function, not monotonically decreasing function. Monotonically, very good example. I am giving star. It just generated in my mind. you always get monotonically decreasing function, but not never get monotonically increasing functions which is bounded. So it is a very exceptional case and very exceptional function. You are looking that this is a monotonically increasing function, and its upper bound is 1 and lower bound is half. So it is a bounded function. So it must have a the theorem states that it must have uh, a subsequence which is convergent. So, or a limit point. So, we are looking this example that we are finding limiting point, but it is true for all the sequence, bounded sequence. That's we have to prove. So, let's see how we can prove this. Prove. I have shown in the example that this is true, but for every case, we can prove this. This can be proved in this way. I am taking nested interval. Nested interval. What is nested interval? Very important to know. Nested intervals. Actually, these intervals very easily uh, can explain any difficult problems. Yeah, that's why nested intervals are very important. You take I a larger interval which is a superset of a I1 which is also superset I2 and that's why and so on dot so on. So you will get at the time in it can be n tends to infinity you can say. So all the intervals in with this relation are called nested intervals. So to prove the theorem we take the nested we take the help of a nested interval. Look first take a we are taking a sequence, bounded sequence. We have, Bolzano-Weierstrass theorem. It is given that the sequence is bounded, and we have to prove that it have a limit point or a convergent subsequence. So look this first that we are taking a sequence Sn Sn taking we are taking that all the points are xn in this sequence. X can be x n r belongs to real numbers. X n belongs to real numbers. Now n tends to infinity and there are infinite number of values which belong to the real line. So now we are since this is a bounded sequence, so we are taking a in infimum or lower bound which is smallest. We are taking we are giving just is and the upper bound we are taking uh, upper bound we are taking s square to make it understand. We if, since all the numbers belongs to real numbers, so s and s prime must be real numbers. So we are taking we are expressing this through an interval. We are taking an interval a and b, a a b interval. A b interval which is called I. This is the I interval. I is a AB interval, closed interval. I is a closed interval, AB interval, where the sequence is represented in this way. Sequence is represented in this way that the lower bound coincide with this uh, uh, interval point A, and the upper bound coincides with the intervals limit interval point B S prime. So now S is equal to A and S prime is equal to B, and this is the interval. Now Xn, there are infinite number of points of Sn, infinite number of points of Sn. So I am taking in that Xn is the nth number of the term of the sequence. So I am taking Xn belongs to now this is the nested interval, first nested interval. So we will divide I by 2 equal parts. Then you will get here this is half and this is also the other half part. So this is also I1, the second I first part of the division after division, and the second part after division. I1. These are all these both I1 are equal. Now, in which interval xn belongs to, we'll take this interval. Now, what will be the figure? Now, the figure will reduce in this way. Now, I am taking there is point C where the division takes place. Then we will get C and B. We will take after every division the interval where xn belongs to. So here xn belongs to, and the interval is C, B, and this is the interval I1. Now I1 again divided by 2. I1 again divided by 2. Then it reduces in this way to this line. It is taken D. So there is a closed interval. There is also a closed interval. And in this way it is divided. So now we will take this is also I2, this is also I2, and this is also I2. So we will take the interval where xn belongs to. So here this interval xn belongs to, we will take CD. So now the next figure will be in this way. This is I2, C and D, xn here, and this will be I2. This is C and D. We will continue this procedure. And at last time at a time we'll get that very small closed interval will get where just xn belongs to, means the figure at the last one, if we continue the division procedure, then one time we'll get such a figure that here xn is in a very closed interval. I am just giving to make understand a just you can understand, but this is not so much uh, lengthy figure. It will be very small figure, and the distance actually of the closed interval uh, tends to 0. So such kind of closed interval we will get. Now we wish to know that xn at this point converges to a point. So how we can prove this? We are taking a neighborhood point x, and we will take an open set or open interval ux where x belongs to the open neighborhood ux. Now look this, ux also, this interval distance also tends to 0. So uh, it take this is ux. This open interval is ux. It is also its distance also tends to 0. Now, but uh, between x and xn, you will get infinite number of points, and both are tending to 0 since. So, mode of xn minus x also tends to 0. So, at the limit point, you will find that, and the interval, if we continue the procedure, I I have doing first I, then I by 2, first first division, then second division I by 2 square, then I by 2 cube, and dot 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 I to the power n. So this tends to 0 because 2 to the power n tends to 0. That's why I am saying that at the last moment the closed interval tending to 0. And the open interval also taken so closer to 0 that just its diameter, interval's diameter are tending to 0. So at this moment, any neighborhood point of xn, the distance between the 2 points or the diameter tending to 0. So limit point of xn must we find that it will be x. So we are very clearly now, found we have very clearly found out that any bounded sequence must have a limit point. Must have a limit. Bounded sequence must have a limit point. And actually it is proved. It have a limit point, and it is also bounded, also convergent, because it is converging to x. Any sequence, bounded sequence, converging to any point. So also in the Bolzano-Weierstrass theorem, it is stated that it must have uh, a subsequence, convergent subsequence. So if your any sequence is convergent, then the collection of any sequence from the main sequence must be convergent. It is actually well known in real analysis that if a sequence is convergent, limit point exists to any point, then the subsequence must be convergent. It is very well known. Sn prime is a subsequence from Sn. It have the same uh, converging point. So this sequence is converging. So subsequence must converge to the same point. So this is very well known in analysis. So we have already proved Bolzano-Weierstrass theorem, and I hope that you have understood through nested interval. This is very nested interval, application of nested interval is very important in analysis. So you have also understood how a nested interval can be used interval can be used to deduce many important theorems in real analysis. So I have already proved Bolzano-Weierstrass theorem. Now let's go in another theorem. This is also important. This is HEINE-BOREL theorem. I am discussing both of two together. That's why it's a region that both are related and equivalent with some property. That's why I am discussing both of them, the theorems together. In Real Access book, you will find both the theorems and their comparisons. So when you go through the book after looking this video, so there you will find out that the equivalents are given. So to make clearly understand, I first prove the two theorems and then try to understand you the equivalence. So what the Ehrenberg theorem states? It states that for a if any if we take any subset from a real number or equilinear space Rn, then uh, two points are equivalent. One that is closed and bound, is closed and bounded, closed and bounded, and another point is that S is compact. Two are equivalent through how we can say that through N-Borel theorem. That two are equivalent. S is compact. If you found that S is closed and bounded, then you will get that S is compact also. And if you find that S is compact, then S must be closed and bounded. But for the case, it must be a subset of Rn. It is the mandatory, not for all. This is must be mandatory. S must be the subset of Rn. If this does not happen, then you cannot prove N-Borel theorem. Mandatory. So you have to keep in mind the S must be the subset of Euclidean space R or R2 or R3. Then you can say. So I am taking just a simple case to prove this. R is the subset of the real line. If it can be proved, then very easily you can prove that other parts is the subset of real line. Now, if S is the subset of R, now I am taking S is compact. What is the definition of compact? I have already launched a video to introduction of compact. Compact means every open cover must have a finite subcover of the set S. So finite subcover. Finite subcover means we take S is equal to, I am giving through interval. It is very easy to prove through interval. This is minus 1 by n 1 by n closed interval where n belongs to natural number. Then this interval you can very easily understand that it is actually open cover of R. So it must have a open cover. It must be, since it is a open cover of R and n can be any value of among the natural number. So it must be the open cover of S because S is the subset of R. So this is the open cover of R. So this is the open cover of S also. So all the collections of such kind of. Now I am broadly all the intervals collection of the intervals. I am giving the collection of the interval minus 1 by n to n. The collection actually this over R. This is the superset R. So super subset of R. So it must be the super subset of S also. It must cover the S. This is what I want to say. So now, since S is compact, it must have a finite subcover. So I am taking that M is a finite number. M is a finite number in R. We know the value of M. So for the intervals through the up to M finite, so this will be the we will get minus 1 to 1 minus half to half. In it is better to give minus 1 1. I am taking complement. It will be much better complement of this interval. So complement of this interval, complement of this interval, and in this way we'll get minus 1 by a 1 by m নিচে চলে এসেছে বাসনপত্রগুলো মাজছে is complement. So these finite number of intervals over S, since S is compact. So we at last find that the complement of this it will be its complement will be what will be. What will be its complement? Its complement will be distance of this distance of this interval is 2 by m. I am again and doing in another way, it cannot be proved in this way, bounded. Anyway, I'm discussing it. Take S is a subset of R. It is it is the collection of the intervals minus 1 by n 1 by n. This is a subset of R. Now, since S is compact, it must have a finite subcover. So I am taking M is finite. So the intervals minus 1 to 1 minus half to half dot all these intervals, closed intervals minus 1 by m a1 by a. All these intervals can cover S. So since S is compact, so that we can look this. We will take the maximum of the closed interval. So maximum of the closed interval is 2. We can look this maximum, because here we will get just distance of this is 1, the distance is 2, the distance is just 2 by m. So so we can very easily look this that uh, actually it is bounded by 2 by m. S must be bounded by 2 by m. So its maximum distance is 2 by m, less than equal to 2 by m. If for this interval is true, if we will take in this way the interval AB, then AB, and we will use a nested interval uh, of the AB, then we will also get that since it's a finite subcover, all the intervals have a finite subcover AI, BI. In that case, we also can prove this that AI and BI are a minimum and maximum of the points in this closed interval. We will take a lot of infinite number of intervals for the open cover and a finite subcover like I just 1 to n. A finite subcover I to m I am taking. Then also we are taking the maximum length, as I have been discussing this, the maximum length. So we will get the maximum of bi minus ai. Maximum of bi minus ai, where I is 1 to m through the finite subcover, not the open cover. Then maximum of this is also finite. So we can say that S is bounded. So any compact set is bounded. Any compact set, any compact set is bounded, and we will prove now that it is closed also. How can we prove that? Any set is called closed if all the limit words belong to the set. If S is closed, then all the limit points of S it belongs to S. So since we are taking that S is compact, so its limit point so all the limit we have to just to prove the S is closed, we have to prove that all the limit points belong to S. So the limit points take a such a limit point does not belong to S. We are taking that S is not closed, just S is compact. S is compact, but S is not closed. A is such a limit point which does not belong to S. Now, how can we prove that? So S is compact, it have a finite subcover. It must have a finite subcover. So we are taking finite subcover like AI is a finite subcover of the open cover where I is 1 to a finite number A. 1 to A. So it is a finite subcover. Now in any of the finite subcover A does not belong to. Then A belongs to the complement of this interval. So I am taking that A belongs to the complement of the EI BI. E does not belong to the EI BI. So A belongs to EI BI, means the complement of the interval. So in one of the point, in one of the interval, interval A belongs to. Now so let A belongs to one of the complement AJ BJ. It is also the complement. So A belongs to this complement. Now one point is you have to note that A is a limit point which does not belong to AJ BJ but belongs to the complement of each. So if we take open sets with A, all the open sets with A like UX, J, all the open sets UXJ of A which is disjoint with AJ interval AJ BJ. Now one point here and the intersection is null. Like this is our assumption. So now intersection is null. So is a limit point. So A must belong to this open sets or open intervals and does not belong to this, which cover the collection of this, cover S. Now, this collection, which is both disjoint, cannot cover S. This collection cannot cover S because here uh, the the collection this uh, intersection cannot cover S because it doesn't have any finite subcover. It doesn't have any finite subcover, so it cannot cover S. So the if you will take example of the figure, E is a point and this is the open sets U A U J A. There are infinite number of open sets and a closed interval. This is the closed interval AJ BJ. The collection of ABJ can cover S, but A does not belong to, if A does not belong to S, then this intersection cannot cover S. So in this, if we will take the open cover and J whereas 1 to n, whereas to 1 to n, 1 to infinity, the open cover, if we take this open cover, this open cover covers S, but this open cover covers S, but it does not have any finite subcover because the intersection found this is not finite, and this open cover we can generate through taking J whereas 1 to infinity. It can cover S, but since S is compact, it must have a finite subcover for every open cover. But this open cover we are generating through intersecting this is the open cover, but it does not have any finite subcover because this is not finite. This is the intersection, and this does not taking the point A. This open cover, this finite subcover not taking the point A. So we are not getting every open cover have a finite subcover. So if, we know that S is a open set, so it must have every open cover have a subcover, but we are generating an open cover which covering S, but it does not have a finite subcover because there is not E. I think I made you understood that this is compact. It must have every finite cover. Every open cover must have finite subcover. So every open cover. This is also an open cover. I am judging, but this open cover by making J 1 to infinity. This open cover uh, have a intersection with the point A. Means there are infinite number of points, closed intervals. or sets. So all are disjoint point A. So this open cover, when we will take the averages 1 to infinity, and we will take the union, when we will take the union of this collection, then both A and S are covered. Both A and S is covered, but when this open cover covers S and A, but since A does not belong to S and this disjoint does not uh, cover point A, so this is a finite. This is a cover, subcover, which is not finite because it if we take I j is equal to 1 to n, j is equal to 1 to m, a finite number of subcovers, a finite number of subcovers, but it does not taking the point A. So one point we will get that it does not it does not mm, cover. So it does not cover. So we are getting that S is not compact, but it is not true. S is compact we have already taken, and it must have every open cover must have a finite subcover. So this is a yeah, this is a contradiction. That's why S must be A must be belong A must the limit point must belong to S. The limit point must belong to S. If if A S is to be complete, then the limit all the limit point must have to belong to S. So S is closed. S is closed. I hope you have understood the tough point to understand that here what is the main diagnosis is that I have to generate a open cover which have not finite subcover with the expression that A is not covered by the finite subcover. It cannot be finite actually. Through this, many points are not covered by A actually. So that's why A cannot be out of S. A must be below A must belong to S. So S is closed. Now this is the Heine-Borel theorem that every compact set must be closed and bounded. Every closed bounded set must be compact, but S needs to be the subset of R. S needs to be the subset of R. I hope you have enjoyed this uh, two theorem, very important in analysis. And thanks for watching. And subscribe this channel to get such kind of videos. Or comment me if you have any problem. Then comment me if you have any other question about this video. Thanks for watching. Have a good day.